Okay, assalamu alaikum. So let's apply today, develop the first law of thermodynamics for open system, which we have developed already in chapter 4 for a steady flow. But let's recall this. So the first law of thermodynamics for a steady flow. So we are considering here a steady flow, and we are talking about the open system for sure. Okay. So for the case of a steady flow open system, we said, let's recall our actually common representation. If we have any system, then we have energy input to the system, part of energy is leaving, and part of energy is stored within the system. Then the first law of thermodynamics, just in general, will be energy out in minus energy out will equal to the change of energy of the system. Like we said, we can also represent the form of thermodynamic in the rate form. So we can say the rate of energy in minus rate of energy out will equal to the rate of exchange of energy within this control volume. And again, Shabab, this term is zero in case when we have a steady flow. Because as we said, in case of a steady flow, the rate of energy input will equal to the same rate of energy output, because we don't have any energy accumulation within the system. Like this, also the mass flow rate. We can apply the mass equation for a steady flow. The mass flow rate in will equal to the mass flow rate out, as long as we don't have any accumulation within the system, or we don't have a change of time within this control volume. But if this term is zero, so in case when we do have a steady flow for open system steady flow, in this case we can say the rate of energy in minus rate of energy out should equal to zero in this case. And this is actually the first law of thermodynamics when we have actually steady flow open system. This term, which represents actually the energy change of the system within the control volume itself, this term actually in case of steady flow, this term will be zero in this case, because actually we don't have a change of time. This energy, Shabab, is the energy of the system itself, which is the internal energy, the kinetic energy, plus the internal energy of the system. And actually, in this case, if you just recall the first law of thermodynamics for closed system, we have considered the general form, the total energy transfer. We didn't consider the rate of energy transfer. Here, actually, for open system, we are considering the rate form. So that actually, when we have the rate of change of time, we can just actually get rid of this term. It will be zero in case when we have steady flow. Now we have actually those two terms, energy in minus energy out is equal to the change of energy of the system. And this actually, Shabab, this form of energy, this represents actually the forms of energy transfer either in or out the system. But actually, this is actually the form of energy within the system itself or inside the system, which we can represent by internal energy, kinetic energy plus potential energy. But what are actually the forms of energy transfer into or out of this system? Energy can transfer in the form of heat, can transfer also in the form when we have work, can transfer in the form of work, and the energy also can transfer due to mass transfer. And we just defined the energy, the term of energy transfer by mass, which is equal to actually the enthalpy of the fluid plus the kinetic energy plus the potential energy of this fluid. But let's substitute here. Then we can say actually energy in minus energy out, it will be Q in, heat transfer in minus heat transfer out, or we can just write it down actually as Q dot net, the net heat transfer to the system. But also we can have work in or work out, then we can say actually the rate of work net to the system either in or out. But why we have negative sign here, we have explained this actually earlier, as the sign of the work into or out of the system is the opposite to the heat transfer. Work is positive when it is leaving the system, but actually heat transfer is negative when actually the heat transfer is rejected from the system. And the reverse actually in case of heat added, it is positive, and actually if the work is applied into the system, it has negative sign. That's why we have negative sign here. But this is actually heat transfer. Energy can transfer by heat, energy can transfer by work, plus also the rate of energy transfer by mass into the system, minus the rate of energy transfer by mass out of this system. All of this actually should equal to zero in this case. But let's define the term of energy transfer by mass and substitute actually in this equation so that we can develop the equation of the first law of thermodynamics for a steady flow open system. We have defined the term of energy transfer by mass as enthalpy plus kinetic energy plus potential energy. Then we can just say Q dot for any steady flow open system, Q dot minus work dot. We can just take those two terms to the other side. So instead of N minus out, it will be out minus N. So that should equal to actually the summation of M dot exit. If we have actually to the system more than one outlet or more than one inlet, then in this case we have to add the summation sign in this case. So to equal to summation of mass flow rate at each exit section multiplied by the enthalpy of the fluid at this exit section plus V exit squared divided by 2 plus G multiplied by Z exit minus the summation of mass flow rate inlet at all inlet section multiplied by actually the enthalpy of the inlet, the enthalpy of the fluid of the working fluid at this inlet section plus V inlet squared divided by 2 plus G multiplied by Z inlet in this case. And this summation sign is just when we have actually a system that have actually more than one inlet and also in case when we have more than one outlet. Inshallah, we'll have this case if we have a system with more than one inlet or more than one outlet. When we talk about the mixing chamber and the heat exchanger, in this case, we should have actually more than one inlet and also more than one outlet in this case. But if we have a single stream, so for single stream, for a system with only one inlet and only one outlet. So in this case, just we have a system, we have one common inlet to the system, and we have actually one common outlet of this system. In this case, for single stream, in this case, actually the mass equation, when we apply mass equation for a steady flow single stream, it will be just mass flow rate inlet is equal to the mass flow rate outlet. And in this case, actually, we can remove the summation sign in this case. But we have mass flow rate in this case, it's the same as mass flow rate outlet, as actually the flow is a steady flow in this case. So we can take it as common, and based on this, actually, we can generate the generalized form of the first law of thermodynamics. In case when we have a steady flow open system, Q dot minus work dot for a single stream, we can take mass flow rate as common, and it will be the difference H exit minus H inlet plus V exit minus V inlet squared divided by 2 plus the gravitational acceleration multiplied by Z exit minus Z exit minus Z. And this is actually the first law, the form of the first law of thermodynamics for a steady flow open system of a single stream. Okay, and we have just developed this equation in chapter 2, but this is a kind of recall for this equation. Let's remind you Shabab with this equation. In this case, actually, this is the rate of energy transfer. We are considering the rate flow. So in this equation, the heat transfer should be substituted in kilowatts. Work, the rate of work also, it should be substituted in kilowatt in this case. We call actually Shabab the rate of work done as power. So when he asks for the power of the system, power mean actually the rate of change. The rate of change actually of the work done or work done in this case. Okay, by mass flow rate, which we have defined actually equal to density multiplied by area multiplied by velocity, and this mass flow rate is calculated actually in kilogram per second. So this mass flow rate is expressed actually in kilogram per second. So this is kilowatt, this is kilogram per second. So that means this is should be actually substituted in kilojoule per kilogram. And those values of enthalpy of the fluid at the inlet and at the outlet, we have learned how to calculate. If the working fluid is steam, I will be using a steam table to calculate H exit and H inlet. If it is refrigerant, I will be using also the table. And if it is air, we have learned how to calculate for gases, how to calculate delta H. We have actually variable specific heat and constant specific heat analysis. And also we have learned how to calculate delta H in case of solid or liquid. So actually we can calculate this term actually as we learned earlier in chapter 3 and chapter 4. But this term its unit is actually meter square per second square, which is equivalent to joule per kilogram. You can just check it. So in this case, we have to divide this term. So don't forget actually to divide this term by actually 10 to the power 3, so that the unit should be in kilojoule per kilogram. Similarly, this term, it will be meter square per second square, which is joule per kilogram. Then we have to divide by 10 to the power 3, so the unit will be in kilojoule per kilogram in this case. Okay. Don't forget also, Shabab, the sign conversion of heat transfer and the sign conversion of the work. Okay, so for heat transfer, it is positive if this heat actually is added to the system, and it should be negative if this heat actually is rejected from the system. And this heat transfer can equal to 0 in case when we have, if he said we have adiabatic system, that means we don't have heat transfer. If he said we have isolated system or insulated system, all of this actually means the heat transfer is equal to 0. Or actually, if the heat transfer is not given or required, then in this case we can consider this term of heat transfer as equal to 0 in this case. So heat transfer is equal to 0 for adiabatic, isolated, insulated system. And also if it is not given or required, then in this case we can just substitute the heat transfer by a value equal to 0. And in this case also, the opposite to this is the work. Work can be positive if it is actually produced from the system, and we'll give example like the turbine, and it can be actually negative if it is consumed by the system. Like in case when we have pump or compressor or fan, all of these devices are actually consuming work in this case. So the sign of the work should be negative sign in this case. Okay. Right. Let's apply this to some steady flow devices. As I told you, most of the engineering devices are steady flow devices. So we'll apply this first law of thermodynamics for some steady flow devices, starting with, let's start with turbine and compressor. Okay, this is the equation that we have developed. We have just developed here. We can express this equation also in the form actually of the specific heat transfer. So in case actually we need to get actually the specific form of this equation, just we can divide by the mass flow rate. Divide the mass flow rate, then in this case it will be Q, specific heat transfer, minus a specific work will equal to H exit minus H inlet plus V exit square minus V inlet square divided by 2 plus G multiplied by Z exit minus Z inlet. Okay, as we have it here, we have Q dot is equal to what? Q dot is equal to the specific heat multiplied by the mass flow rate. And like this also, the power, which is the rate of work done, is equal to actually the specific work multiplied by the mass flow rate. Okay, we have defined earlier that Q is the work per unit mass. Okay, or we can, it is actually work dot the rate of work per the rate of mass. Or we can say actually the work dot, sorry, this is Q dot. Q is equal to Q dot divided by M dot, or we can say Q dot is equal to actually the specific energy, the specific heat transfer, which is in kilojoule per kilogram multiplied by the mass flow rate, which is kilogram per second. Then the heat transfer in this case will be calculated in kilowatt. Okay, so we can get another form. We call the specific form for the first law of thermodynamics. In case actually the given are given actually in the specific form kilojoule per kilogram, then we can apply this form of the first law of thermodynamics. Based on this conversion, rate of work is equal to the specific work multiplied by M dot, and rate of heat transfer is equal to the specific heat transfer multiplied by M dot. So we can just replace actually the work dot and the Q dot by those values and divide the whole equation by M dot. And in this case, we can get this form. Okay. So this is a again. This is all terms should be in kilojoule per kilogram. If we divide here by 10 to the power 6. Okay. Type, let's apply this equation to some steady flow devices, starting with turbine and compressor. So inshallah we'll be considering different steady flow devices: turbine, compressor, nozzle, diffuser. We'll talk about heat exchanger, mixing chamber, throttling valve, and many devices inshallah we'll tackle actually in this course. Okay, in this chapter. Okay, but let's start with some steady flow devices. So the application of the first of thermodynamic or a steady flow open system. So let's consider some steady flow devices, starting with turbine and the compressor in this case. Okay. The idea of the main difference between turbine and the compressor. So in case of turbine actually receive flow of high pressure and high temperature. So actually the input energy to the turbine, we call it actually flow energy, which is fluid at high pressure and high temperature. Or we can say fluid of high enthalpy, okay? Which is internal energy that represents the temperature, and also the term actually of flow energy, which represents the pressure in this case. So we have flow of high pressure and high temperature coming into the turbine, then this turbine it expands to the turbine, then out of this turbine actually we can generate shaft power in this case. So the function of the turbine is to convert the flow energy into actually mechanical energy. So this shaft power is a form actually of mechanical energy of the fluid. Okay, and we said the idea of the turbine actually consisted actually of rows of fixed plus moving blade. Each fixed blade, row of fixed blade, is followed by actually a row of moving blade, and the fixed blade takes the shape actually of nozzle. So in this case, this is actually we call the fixed blade of the turbine. It takes the shape of nozzle. So in this case, we have a flow of high pressure, flow of high temperature is just going inside this nozzle. So what will happen in this case? The area is contracted in the flow direction, but actually it is a steady flow open system, so mass flow rate is constant. Mass flow rate is density by area by velocity, and this is actually constant at any cross section. So when the area is reduced in the flow direction, that means in this case for fixed mass flow rate, then in this case the velocity of the flow will be increased in this case. Then we can convert this flow energy, we can convert it into kinetic energy, flow of high velocity. Then this flow actually can hit the moving blade of the turbine, which is a kind of impeller, and this impeller also has blades. So the flow will be coming here and hit those blades, then we can generate, in this case, we can generate shaft power, and the shaft in this case can start rotating, generating the mechanical power out of this turbine. This part, as we said, the nozzle, we call it fixed blade because it is fixed, not actually rotating. But in case actually this part, we call it actually, we have here moving blade because in this case they are fixed to a rotating shaft. So this impeller, we call it actually as the moving, the blades actually on this impeller of buckets, we call them actually as moving blades in this case. So any turbo machinery system, either turbine, compressor, anything fan, it should have actually turbine or compressor. Then in this case, it has to have fixed blade, and it has to have also moving blade. And the function of the turbine is to convert actually the flow energy of high pressure and high temperature, convert it actually into mechanical shaft power in this case. And the reverse, however, is the case actually when we have pump. So in case when we have pump or compressor, the same function actually in this case. So pump or compressor actually require input shaft power. So we have the input energy is the mechanical energy in this case. So we have a rotating shaft, and at the outlet actually of this compressor, we can have actually a flow of high pressure, or the main function of the compressor or pump is to raise the pressure, and when we raise the pressure, the temperature also will be raised as well in this case. So what we get out of the pump, we get actually a flow energy in terms actually of a flow of high pressure, and this is the main function of the pump and compressor. Pump is dealing with liquids, and actually compressor is dealing with gases. Okay. And in both cases, we have to have also fixed blade plus moving blade. But in this case, actually, the pump, in order to raise the pressure of the flow, then in this case, we have to have a rotating shaft in this case that takes the flow, and then it can compress it actually to a high pressure in this case. So turbine converts the flow energy into mechanical energy, but pump or compressor convert actually the mechanical input energy in terms of shaft power. It can convert actually to flow energy in terms actually of flow of higher pressure. Like before, we can go ahead and study pump, turbine and compressor. Pump is very similar to the compressor, the same function, but pump is dealing with liquids and compressor is just dealing with gases. Okay. Let's first of all talk about the turbine as well. Just I will give you an idea of the different type of turbines. We have turbine actually are divided into steam turbine or gas turbines. Okay, a steam turbine and the gas turbine, the difference actually is the working fluid in this case. In case of a steam turbine, which is used in a steam power plant for electrical power generation, in this case actually we have water. Water is coming to this pump under low pressure. So the function of the pump is to raise actually the pressure of this liquid water into the pressure actually of the boiler. This is actually the boiler. Inside this boiler we have a combustion chamber in which actually we add heat, we burn the fuel, then we can generate heat. This heat actually is added to this liquid water. So what will happen to the water? Water will be evaporated and it will be converted to steam. This is steam under high pressure and high temperature. Now we have a flow of high pressure and high temperature. Then we can expand this flow inside the turbine of fixed blade plus moving blades. Then we can generate actually shaft power output of this turbine in this case. And the steam in this case, the process through the turbine is expansion process. So the pressure is reduced. Then in this case, the pressure will be reduced and temperature of the steam will be reduced. That means actually this steam will be condensed in this case. And usually the steam leaving the turbine is a saturated mixture of liquid plus vapor. But in order to repeat this cycle and generate continuous shaft power in this case, we have to return to the same initial point. We have to get back the same initial point of water. We need liquid water only. We don't need saturated mixture. So in this case, we have to cool down actually this saturated steam inside what we call actually a condenser. Condenser is a heat exchange. Steam will be passing inside the condenser, and then we can have some cooling water through an external circuit here. This we call this actually as cooling water, which is the techniques used actually in a steam power plant. Then we can pass this cooling water actually around this steam inside the condenser. It will absorb heat in this case. Then steam will be rejecting heat inside the condenser and it will be converted to again to liquid water. Now we can handle this liquid water and then it can repeat the cycle again. In this case, Shabab, we call this turbine as a steam turbine in this case. So this is what we call the steam turbine because the working fluid in this case is steam. Okay. Like we have another kind of turbine which is called actually the gas turbine. In case of gas turbine, the working fluid actually is the exhaust gases of the combustion process. And the gas turbine, if you have, the idea is to have a compressor connected on the same shaft on a turbine, on a gas turbine. And air is coming, so we have air is coming into this compressor, usually at low pressure and low temperature. Usually it's atmospheric condition, okay? And this air actually is just raised inside this compressor to high pressure and also high temperature. As the pressure will be raised, then in this case the temperature will be raised, okay? So the pressure will be raised in this case up to the combustion chamber pressure, the pressure of the combustion chamber. We have combustion chamber here. We have this is air at high pressure. Then we can add fuel and burn this air plus fuel inside this combustion chamber. Then in this case the exhaust gases will have here exhaust gases of high pressure and also high temperature. Now we have fluid of high pressure and high temperature. Then we can just take this fluid and pass it inside the turbine to expand from high pressure to low pressure. Then in this case, we can generate shaft power in this case using this flow. And then the exhaust gases will be just actually left to the atmosphere in this case. And then we can repeat the process, take air again, and then we can repeat actually this cycle. This kind of cycle, a steam turbine cycle, is a closed cycle. Okay, just the working fluid is circulated. It evaporates steam and then condensed to liquid water and then repeat, but the same working fluid. This is actually a closed loop cycle, open system. Here actually it is open loop. This is actually the fluid, the air that we extracted from here, plus the fuel has just been exhausted. And then we can repeat the process, take another actually amount of air and repeat the process in this case. And in this case, Shabab, part of the shaft power of the turbine is used actually to run this compressor on the same shaft. Okay, so the input power to the compressor is coming actually from part of the output power of the turbine in this case. And the net work of the cycle is the work of the turbine minus the work of the compressor. And here for the steam turbine, the net work for the cycle is the work of the turbine minus the input work to the pump. Pump also similar to compressor, it needs input shaft power in this case. Okay. Type we have also, so turbine are steam turbines, the working fluid is steam, so I will be using the steam table. Or gas turbines, the working fluid is a mixture of air plus fuel or exhaust gases. We can assume exhaust gases as air, and we can use the air table, which is table A17 in this case, to calculate the properties. If it is in your exam, I will just tell you which table you have to use and about the assumption to assume the exhaust gases as air. Okay. But here also the gas turbine has another classification. Gas turbine can be stationary gas turbines. We call them stationary gas turbine, which is used actually in electrical power generation. Like the cycle that just we have represented, we can connect the shaft out of the turbine to a generator, electrical generator, then we can actually generate electrical power in this case. In a steam power plant, we call the plant as combined cycle for electrical power generation when we have both actually gas turbine are applied. The steam turbine is working beside the gas turbine in this case. So we call the power plant in this case as a combined power plant because it combines between the steam turbine, combines between using a steam turbine and gas turbine in this case. Okay, so we call it as a combined cycle. Usually steam turbine, Shabab, to start a steam turbine, it takes around 2 to 3 days to start a steam turbine. So usually steam turbine are continuously running. But what about the electrical load, electrical power? So at noon here in Saudi Arabia, the electrical power actually consumption is the highest. But actually at night, this electrical load, actually the required electrical power for consumption is just reduced. So in this case, we can run a steam turbine to give actually the basic load that does not actually change, like actually the minimum load, which is we get actually at night. But what happens actually at the noon time when this actually requirement of electrical power consumption has just been raised? In this case, the gas turbine is easy to start, just a switch and you can start it. Then in this case, you can run actually the gas turbine to give you the extra required load in this case. So we can run a steam turbine to give fixed load because it takes a very long time to start a steam turbine, 2 to 3 days. But actually, if the load is changing during the day, the required electrical load, then in this case, we can use gas turbine actually to provide the additionally required load in this case. By gas turbine, we have two kinds, the stationary gas turbine, which is used in electrical power plant, and also we have the gas turbine actually that is used in jet engines. So in case of jet engines, we have compressor connected on the same shaft with the turbine, and here we have the combustion chamber in between, and the same process actually. It takes the air, and then we have actually the exhaust in this case. But in this case, we don't need shaft power out of this turbine. Just in this case, we have gas under high pressure and high temperature, this gas will be partially expanding inside the turbine just to generate shaft power that is enough to run this compressor. So this means actually those exhaust gases leaving here is still the exhaust gas under high pressure, under high temperature. Because we have partial expansion in the turbine in this case, just as a function of the turbine is just to provide power to run the compressor. So that means the exhaust gases are still under high pressure and high temperature. In this case, we can put the whole gas turbine inside what we call the jet engine. This is a kind actually of a jet engine. Usually is like the engine shabab in the aircraft, the civil aviation aircraft. If you look at the engine, which is a gas turbine engine, you see the end section to this engine take actually the shape of diffuser. Why diffuser shabab? So if we have diffuser, in this case the area is increasing in the flow direction, and we have a steady flow, M dot density by area by velocity. If the area is increasing, then in this case the velocity of the flow will be reduced. And based on Euler equation, delta V minus rho V delta V, in this case the pressure is the opposite, actually is opposite function of the velocity because we have negative sign. So pressure is proportional to 1 over velocity. So whenever the pressure is raised, the velocity will be reduced. Velocity is reduced, in this case the pressure will be raised in this case. But in this case pressure, with the area increase in the flow direction, velocity will be reduced, and the pressure in this case will build up within the system. So the function of the diffuser here, the inlet section, is just actually to enhance the pressure of the air. Then air actually is passed through the compressor to raise its pressure, and then we have fuel here to burn, to have exhaust gases, and then the gases will be leaving the turbine. As we said, we have partial expansion here. Then in this case, the gases is still the exhaust gases under high pressure and high temperature. Then we can pass the exhaust gases inside actually a nozzle. This is actually the tail section of this jet engine, represent actually the design of a nozzle. Nozzle, that means actually the area is reduced in the flow direction, so the velocity in this case will be increased in this case. And based on this, actually we can get actually a thrust force in the reverse direction. This force actually is equal to, based on Newton's second law, is equal to the rate of change of momentum, which is dmv by dt. Okay, and that's why actually the airplane is just moving forward. This movement actually, or the flying of the aircraft, is due to actually the generated thrust equal to the rate of change of momentum. So as we increase this, the velocity of the flow leaving the tail nozzle, so that means actually we have higher thrust force in this case, which is function of the rate of change of the momentum based on actually the Newton's second law. Very simple example actually of this thrust force. If you have a balloon or something, just actually fill it with air. Then in this case, just tip actually or stick your hand actually on the opening and then just leave it. So when you leave it, actually the air will start leaving with high velocity, and you'll find actually the balloon is moving in the reverse direction. And this is a simple example of the thrust force when we have actually a rate of change of momentum. Then in this case, we can generate a thrust force in this case. Okay, but this is regarding the turbines. Okay, fine. What about the compressor? I'm just giving you an idea. Such details are not given in your slides, but this is to understand. Inshallah, I will have a detailed course on turbo machinery. I think we will be talking more about turbine and compressor. But in case of compressor, we have actually two kinds of compressor. We have centrifugal flow compressor, and we have axial flow compressor. Okay. In case of centrifugal flow compressor, as we said, compressor, any turbo machinery device should be consisting actually of fixed blade and moving blade. Okay, so in this case, we have an impeller or a casing, something like this. So this is the impeller actually. The flow is coming into this impeller in the axial direction, which is normal to this form. Flow is coming axial. and then actually the flow is leaving in the radial direction between the blades. So here, those are the blades of the impeller. This impeller, we call it actually as the blades on the impeller, we call them as actually as moving blades. So this is actually the moving blades attached to the impeller. Flow is coming axial, normal to this form. So the flow to this compressor, and it leaves actually in between the blades. And then actually it is collected here in this clearance between the impeller and the casing. Casing, if you have the outer, this is the outer casing, which represent actually the fixed blade, okay, which is fixed. The outer casing is fixed. Then the flow is moving actually through this clearance until actually it is leaving the compressor of high pressure in this case. Okay, so we need mechanical shaft power first of all to run this impeller, and then the air actually will be passing between the blades. If you look at the area between the blades, the area between each two blades, you see the area is taking the shape of diffuser. The area is increasing in the flow direction. So that means area is increasing. As we said again, mass flow rate is density by area by velocity. So as the area is increasing, the velocity will be reduced. And as the velocity is reduced, then the pressure will build up within the system. So the area between the blades takes the shape of diffuser, so the pressure will build up within the system. Even this clearance, when the flow actually is going through the clearance, the area of the clearance also is increasing in the flow direction in this case. So it's a kind of this representation, okay? The area in the clearance between the impeller and the casing is also increasing in the flow direction. So that means actually the pressure will build up within the system in this case. And we call it central flow compressor because the flow is coming axial and leaving in this case in the radial direction. So flow is coming axial and leaving radial. And in the design of the compressor, you will find actually the shape, the area between the blades takes the shape of the diffuser so that the pressure can build up within the system. What about the axial flow compressor? It also consists of impeller. This is the impeller. Attached to this impeller, we have the moving blades are attached to this impeller. We have different rows actually of moving blade, and around this impeller we have the casing, which is the fixed blade or the casing of this impeller. So the flow in this case in the axial flow compressor is coming axially, and here actually you will find first of all we have those are the moving blade, and fixed to actually to the casing we have actually the blade. So between each row, two row actually of moving blade, we have fixed row of fixed blade is attached actually to the system, and so on. So here actually we have row of fixed blade attached to the casing, and so on, until the flow actually also is leaving in the axial direction. So when the flow comes to this compressor, it will find the area between the impeller and the fixed blade takes the shape of diffuser. Also when it comes here, between this moving blade and the casing, the area also is increasing in the flow direction. So in this case, actually the pressure will be building up through the system until actually it leaves here in the axial direction and of high pressure. We call this as axial flow compressor because the flow is coming axial and it is leaving also in the axial direction. And in this case, we have to have what? We have to have for the compressor input shaft power to rotate this impeller, and in this case the output actually is the flow energy in terms of high pressure.